Next are the applications of Nernst equation. Yesterday I told you about the Nernst equation and we derived that equation, and now we will study their its application, that how it is applied and what the information does it give us, that Nernst equation give us. So first application is calculation of electrode potential of single electrode. So first application is calculation of electrode potential of single electrode. So how electrode potential of single electrode is calculated with the help of Nernst equation. So for a general reaction, for example a general for general reduction reaction, that is for Mn positive cation, n electrons are coming and they are reducing it to the M, that is metal. So the Nernst equation can be written in two ways for the above reaction, and these two ways are Mn positive oblique M. Electrode potential of this reaction can be written as E naught Mn positive oblique M plus RT NF ln Mn positive M. So this is the Nernst equation for the single electrode reaction, and further this equation can also be written as E naught of Mn positive oblique M minus RT NF into ln M oblique Mn positive. So what is the difference between these two equations? Here difference lies at the numerator and denominator. Here there in first equation there is positive sign and Mn positive oblique M is the equation, whereas in second equation the numerator and denominator has changed their respective position with each other and the sign has been changed to the minus. This is negative sign. So we will use only the first form in further discussion, converting natural logarithm to log raised to power 10 in the first expression. So we will use only this equation, and further it can be written as E Mn positive M is equal to E naught Mn positive oblique M plus 2.303 RT oblique NF into log of Mn positive oblique M, concentration of Mn positive cation oblique M. So you can understand it by let me write a simple equation. Na positive is attaining an electron and getting converted into the sodium, and you have been provided with certain concentration of the sodium and sodium positive cation. So it means simply this, that these metal ions are written this Mn positive and M form. So here Mn positive oblique M is the electrode potential, standard electrode potential with reference to standard hydrogen electrode when concentration of Mn positive is 1 mole per liter, and value of R is 8.314 joule per Kelvin per mole. So what I am saying that suppose that concentration of Mn positive is 1 mole per liter and value of R is 8.314 joule per Kelvin per mole per liter. T is the temperature, Mn positive is the molar concentration of ion, this is 1 mole per liter. N is the number of electron, that is number of N is the number of electrons gained. F is the Faraday constant of 96500 coulomb per mole, and M is the concentration of the metal. Capital M is the concentration of the metal. So after putting all these values in this equation, we will get E value of Mn positive oblique M is equal to E naught of Mn positive oblique M plus 2.303 into R. Value of R is 8.314 into temperature at standard conditions. The temperature is 298 Kelvin, that is 25 degrees Celsius, divided by NF. So value of N can be written as per metal, that is if there is sodium is gaining 1 electron, so value of N is here 1 electron. Suppose if there is calcium is gaining 2 electron. To get reduced, so value of N will be the number of change in the electron. So N is the value, and further value of F is 96500 coulomb per mole. So after calculating all these values, we will get E naught Mn positive oblique N plus 0.059 oblique N into log of, sorry, I forget to write here, log of Mn positive oblique M. So it's log of Mn positive oblique M. So for in general, for any electrode, we can write it as, this is generally reduction reaction, this was generally reduction reaction, so we can write here as electrode potential for reduction electrode potential of particular electrode is equal to standard electrode reduction potential of that electrode. E naught means the standard plus 0.059 oblique N into log of concentration of, this is oxidized state, and concentration of reduced state. So this is the way how can we calculate this is the way by which we can calculate the electrode potential of single electrode. So you can very easily calculate the electrode potential of any single electrode by above method. So if you have been provided with concentration, I told you this yesterday also, that if you have been provided with the concentration or standard reduction potential of electrode or any of these values, you can derive the other related values. Value of N can be written from the particular chemical reaction, that how many electrons are undergoing change. So this is the method to calculate the different electrode potential of a single electrode for the different electrodes. So next is the application of Nernst equation in calculation of equilibrium constant. So next is the application of Nernst equation in calculation of equilibrium constant. So Nernst equation for a reversible cell in the state of equilibrium is written as E of cell is equal to E naught of cell minus 2.303 RT oblique NF into log of K, where K is the equilibrium constant. So equilibrium constant, I had explained you the equilibrium constant in chemical equilibrium chapter. So suppose a particular electrochemical reaction is taking place as zinc solid is converting into zinc 2 positive, that is zinc sulfate aqueous with the salt bridge, and copper sulfate aqueous is further converting into copper solid. So in this cell, zinc act as an anode and copper act as a cathode. How? zinc is undergoing oxidation, zinc 2 positive plus liberating 2 electrons, and copper is gaining 2 electrons to get reduced. So this zinc is acting as anode, oxidation takes place at anode, and copper is acting as a cathode as it is undergoing this reduction. Copper 2 positive is converting itself into copper metal. So the electron flows from zinc to copper in the external circuit. This I had also explained this zinc copper electrodes when I was telling you about the electrochemical cells in the initial lectures of this chapter. So as the cell reaction takes place, the concentration of zinc sulfate increases with time while that of copper sulfate decreases. Why? Because zinc is undergoing oxidation and converting itself into zinc 2 positive, and zinc 2 positive is present in zinc sulfate. Basically, what is zinc sulfate? Zinc sulfate is zinc 2 positive plus sulfate ion. So as the reaction proceeds, the concentration of zinc sulfate increases and concentration of the copper sulfate decreases, because copper from this copper sulfate is undergoing reduction to get reduced to the copper solid. So at equilibrium, the two electrode potentials become equal and the EMF of the cell becomes the zero. EMF of the cell becomes zero at equilibrium. I am just writing here K. So at this stage there is no flow of electron from anode to cathode in the outer circuit, hence the cell stops the working. So this is the equilibrium state when cell stops working. Why cell stops working? Because there is no further oxidation of zinc to zinc 2 positive, and there is no reduction of copper 2 positive to copper metal. So the cell has attained the state of equilibrium. So at equilibrium, what does happen? Zinc solid plus copper 2 positive aqueous changes to zinc 2 positive aqueous plus copper solid. So the equilibrium constant for the above reaction can be written as K is equal to zinc 2 positive into copper divided by copper 2 positive into zinc solid. So this is the basic definition of equilibrium constant. What is the basic definition of equilibrium constant? The equilibrium constant of a particular reaction is equal to the product of the concentration of the products raised to power their stoichiometric coefficient divided by product of the concentration of the reactants raised to power their stoichiometric coefficient. So here stoichiometric coefficients are 1 for all the reactants and products. So there is no significance of writing or no need of writing this one in the power form. So where zinc 2 positive and copper 2 positive are equilibrium concentrations. So since we take the concentration of the metals is equal to 1 mole per liter, so the concentration of this copper solid and zinc solid is 1 mole per liter. So the above equation reduces to zinc 2 positive divided by copper 2 positive. So putting the value of K in the first equation, that is in this equation, we gets the E value of cell. EMF of a cell is equal to E naught of the cell minus 2.303 RT over NF into log of zinc 2 positive divided by copper 2 positive. So this is the modified form of this first equation. Further, at equilibrium, what happens at equilibrium? At equilibrium, EMF of the cell becomes 0. So value of this thing also becomes 0. This term also becomes 0. So we can write this equation in further modified form. E naught of a cell is equal to 2.303 2.303 divided by 2.303 RT NF into log of zinc 2 positive over copper 2 positive. So zinc 2 positive is the, what is zinc 2 positive? It is the product, and copper 2 positive is the reactant in their oxidized form. So we can write zinc 2 positive oblique copper 2 positive. So you can remember it as product in the oxidized form divided by reactant in the oxidized form. So further this equation becomes, this can be written as 1, and further at 25 degrees Celsius, that is 298 Kelvin, and when then value of R will be 8.314 joule per Kelvin per mole, value of F will be 96500 coulomb. So putting these values in equation, we get E naught of cell is equal to 0.059 divided by N into log of K. So it becomes as, so this is the how the equilibrium constant is determined by with the help of Nernst equation in case of a cell. So you can be asked in exam that determine the expression to determine the value of equilibrium constant with the help of Nernst equation in case of a cell. So you will derive this equation with the help of all the all this methodology. So simply you must, first of all you must remember that what is the Nernst equation. First of all write the Nernst equation, then give an example. You can give example of any electrochemical cell in which there is a redox reaction. So I wrote here the most common example of the electrochemical cell. Here zinc is undergoing oxidation and copper is undergoing reduction. Zinc is undergoing oxidation at anode and copper is undergoing reduction at the cathode. So zinc sulfate exists as a zinc 2 positive and SO4 2 negative, and copper sulfate exists as a similarly copper 2 positive and sulfate 2 negative. So at equilibrium, what happens at equilibrium? Cell stops working. Why? Or the EMF becomes 0. Why? Because at equilibrium all the zinc is oxidized to zinc 2 positive and all the copper 2 positive is reduced to copper. So there is no further scope of further reaction. So cell stops working, or we say in technical terms the EMF of the cell becomes 0. So at equilibrium, what happens? At equilibrium, this equilibrium is established in this reaction as zinc is converted into zinc 2 positive aqueous and copper 2 positive is converted into copper solid. So equilibrium constant can be written for the above reaction as, because by definition what is equilibrium constant? Equilibrium constant is the product of the concentration of the product raised to power their stoichiometric constant divided coefficients divided by product of the concentration of the reactants raised to power their stoichiometric coefficients. Further further the concentration of these metals are taken as 0 by 1 by convention. So putting the value of these copper solid and zinc solid 1, our above equation reduces to this equation. So putting the value of K in this equation 1, we write it as this way. And further at equilibrium the EMF of the cell becomes 0 as I told you earlier. So putting the value of E of cell, EMF of the cell 0, the further equation is simplified as, and zinc 2 positive over copper 2 positive. Further at 25 degrees Celsius or 298 Kelvin, value of R is 8.314 joule per Kelvin per mole, and the value of Faraday is 96500 coulomb. So putting all these values, we get this equation. So this is the application of Nernst equation.